Okay, this section, I gotta warn you, it's a little more beefy. There's kind of more to it. It's a little more complicated than the previous section, so I guess it kind of makes up for the shortness and the sort of easiness of the previous section. It's not too bad. It's just a lot more thinking involved. And anyway, so okay, this section is titled Applications Involving Quadratic Equations. And we probably know by now that the word applications is kind of code word for word problems. But they're not too bad in this section. I think they kind of just revisit concepts that we've seen before. Like if you remember, we've seen problems where we calculate things that relate to distance, rate, and time. Remember, distance equals rate times time, d equals rt. And then work, like if two people are working together versus separate, how long will it take them to complete a job? So let's just revisit those types of problems. It's just that the equations we get once we set them up will be they'll be quadratic equations. So in previous sections where we saw those types of applications, they've kind of avoided the types that once you set them up, they'll be quadratic, because we didn't know how to solve quadratic equations until now. But the first application, before we get to that, is what we're going to do is go back. We've seen this before where we just take a formula and solve it for a certain variable. But I guess the new thing here is that we haven't really solved a formula for a variable where that formula kind of has a quadratic form, or it has a square, you know. And so let's see, and there's not really, I don't know, anything to really worry about or anything to tell you beforehand. You just kind of gotta dig deep and try to remember how we did it before. So the first, very leftmost example here, we have a formula, and I always like to add this because it makes it more interesting. The following formula represents the surface area of a sphere. So if you kind of think about a sphere, like, I don't know, a ball, like a basketball or something, it looks, you know, two-dimensional when you draw it, but imagine it's three-dimensional. So the surface area is like the outer part of the sphere, you know? Like a basketball, it's hollow, right? There's nothing inside. So it'd be kind of telling you how much material was used for that basketball. Even though it's a three-dimensional figure, you're only measuring kind of a two-dimensional thing, because if you take the material that the basketball or any kind of ball is made out of and you lay it flat, it's just a flat piece. It's not really three-dimensional. So kind of interesting, but if you want to know the surface area of a sphere, it's the area equals 4 pi times r squared, where of course you can probably guess r is the radius of the sphere. The distance from the outer part to the very middle. Okay, and they want us to solve for r. So if you remember from before, all you do when they say solve this formula for this variable, you take that formula and you can multiply both sides by stuff, you can divide both sides, add, subtract. You can square now, you can square root. Those are kind of our new tools that we have. You just want to isolate that variable. So when they say solve for r, in the end I want to see r equals blank. And whatever the answer is, that's my answer. Or whatever's on the other side from r, that's my answer. So I'm looking at a equals 4 pi r squared, and I'm thinking, okay, how do I get r by itself? Well, the first thing I think I want to do is what? You know what? One way to think of it, if you're thinking, okay, but how do you know what order to get rid of things in? You know, the way I remember it too is you want to get rid of things, like, I know I want to move the 4 and the pi and the square eventually. I know that there's a certain order I have to do it in. You want to get rid of things in reverse PEMDAS order. So, you know, when you're simplifying something, like you have an expression and you want to simplify it, use order of operations, parentheses, exponent, multiply, divide, add, subtract. But when you're trying to move things over to isolate a variable like we are, you kind of want to go backwards. So the add, subtract, that's the first thing you would want to do. If there's anything adding or subtracting, you want to get rid of that first. And then the multiply and divide. Anything multiplying or dividing, you want to get rid of that next. The third, what comes next? Exponent. And then the last thing you would want to do is get rid of anything inside the parentheses. So I'm going to look at what do we have. Do I have anything adding or subtracting next to my variable in what we have? No. So I can skip that step. Do I have anything multiplying or dividing? Yes, actually the 4, the pi, they're both being multiplied by r. So my first step would probably be to get rid of those guys. And of course you want to do the opposite to get rid of it. Since they're multiplying, I'm going to divide. And you know what? You can divide both at the same time. You could divide by 4 and pi. That'll kind of knock them both out at the same time. And of course, the other side of the equation, you always end up with something really ugly. So don't expect the other side to look pretty. It's like one side looking better, the right side, it's looking simpler, but the other side's going to be sacrificed and look worse and worse. Alright, so we've gotten rid of what's multiplying or dividing. We're done with that step. Now, how about any exponents? Well, yeah, that's the last thing to get rid of, so that's what we'll do last. And there are no parentheses, so I don't have to worry about that. So we've seen by now, how do you get rid of a square? The opposite of a square is a square root. So we'll square root both sides. But remember, when you square root both sides of an equation, you have to put a plus or minus next to the, I guess, we used to say the numerical part, but I guess the side that doesn't contain the variable you're trying to solve for. And now we have r by itself, so that must be our answer. Plus or minus the square root of capital A over 4 pi. And I think I mentioned this before, but it's probably worth saying again. Be careful because the homework is case sensitive. So if you put a lowercase a, they're going to mark it wrong and not tell you why. So keep that in mind. If you see you got something wrong and you're wondering why, make sure you check, was it supposed to be a capital or a lowercase? Anyway, so that should be your answer there. All right. So far, so good. Let's try the next one here. The next one, that's an interesting concept too. The formula that's coming next, it represents the number of phone calls between two cities where the cities have populations Q1 and Q2, and they're S miles apart. So that's kind of interesting. You can kind of, I guess some people calculate about how many phone calls will happen between two cities based on their populations and how far apart they are. So anyway, we have this formula and they want us to solve for S. Okay. Let's see, this is one, I guess this one's a little more unique, and we might see this again in the future, but we have a formula where we're solving for a variable that's in the denominator. So I think we've seen this before. I mean, let's see. I guess if you know that your variable's in the denominator, you want to get it out of the denominator. Because, in the end, I want to see S equals something, and that'll be my answer. But as it is now, S is in the denominator. I can't really solve for S if it's in the denominator. So I want to get rid of, or get my variable out of the denominator. To get your variable, whatever one you're trying to solve for, out of the denominator. And we haven't had to worry about that in the first example. There was no denominator. But if you do see one, you want to multiply both sides by the LCD, which we saw actually in a chapter, the Rational Expressions chapter, way back when. Both sides by the LCD. Yeah, whenever you just want to clear fractions, I just wish this, I wish this problem had no denominators. Just multiply both sides by the common denominator. And in this one, there's only one denominator, so that guy will be the common denominator. I'm just going to rewrite it real quick. Multiply both sides by s squared, because that's the denominator. This side and this side. So on the right side, if you think of that, s squared is over 1. It's going to cancel with the denominator s squared, which was the whole point. I brought s squared over to the left side instead of the right side, which is good because now it's in the numerator as opposed to the denominator. And on the right side, you're just left with whatever was in the numerator. The k, the q1, and the q2. Alright, so now it's kind of confusing because the variable you're trying to solve for popped up on the other side. But now that it's in the numerator, we can kind of go back to these steps we were talking about in the previous problem, where you want to get rid of things. If I want to isolate s, I need to get rid of n and the square that's on s. But I want to do it in a certain order because, imagine right now, what if I square root both sides? If I square root this, actually that square root and the square won't cancel. Because a square root and a square only cancel if the entire thing under the square root is being squared. But there's a piece of it that's not being squared. N doesn't have a square. So square rooting right now would not help, and it wouldn't cancel that square, unfortunately. So we should follow these steps, the reverse order of operations. Not square rooting, okay. So first thing it says is you want to get rid of anything adding or subtracting first. Well, on the left side, there's nothing adding and subtracting with s, so I can skip that. Is there anything multiplying or dividing? Yeah, that n is multiplying by s. So I'll divide by it to get rid of it. There he is. So that'll get rid of it, and that way s squared is all by himself on the left side. On the right side, there's not much I can do. I don't really know what any of these things are. They're all just variables, so I could just leave it like that. And then there's only one thing to get rid of, the square. And we know how to get rid of a square by now. It's a square root. I'll square root both sides. And this time, now finally, the square root and the square will cancel. That's because there's only, all that's underneath the square root is being squared. Not like when it was s squared n. So s is by itself now, but don't forget you need a plus or minus whenever you square root both sides of an equation. And there's nothing I can do to simplify this. I'm just going to leave it all under a big square root, and that's it. Okay, let's try one more here. This last one, or no, not the last one, the second to the last one, sorry. The application, it's the speed of a car based on the length of the skid marks. So that's kind of interesting. If you were to brake really hard in your car and you made skid marks, someone can tell how fast you were going based on this formula. So that's kind of scary, actually, right? If you, I guess if a police officer pulled you over and said, you were going way too fast, look at your skid marks. I mean, you might think, how do they know that? There's no way how they know how fast I'm going. But there is a way, and that's why, you know, when there's a really bad car accident, a lot of times they have all these technicians come and take measurements and stuff, because they're going to figure out whose fault it was, who was going too fast, who was, I don't know. So you think, like, no one saw it, so no one will know if it was all my fault or something, but they'll figure it out. Anyway, sorry, I got to go off on a tangent, because that's kind of interesting. So they want us to solve this equation for L. All right, we have R equals 2 square root of 5L. All right, well, looking back at those steps, we want to go backwards with the order of operations. So first thing I want to do is kind of get rid of anything adding or subtracting, but there's nothing. So how about anything multiplying or dividing? Well, you know, the kind of tricky thing on this one is L is being multiplied by 5, but it's kind of like the L and the 5 are both trapped inside this root. So you couldn't really get rid of that 5 right now. He's trapped in the root. I think I'm going to have to get rid of the root first before I get rid of the 5. On the other hand, though, I do see that 2 is being multiplied on this side, so I can get rid of that guy by dividing it. It's just that the 5 I can't really get rid of yet because it's stuck inside the square root. But the 2 I can get rid of. It'll be r over 2 equals now just the square root. Okay. And now, like we were talking about, I can't get rid of the 5 yet because he's stuck inside the root. Maybe if I get rid of the root, that'll work. So what's the opposite of a square root? That would be square. I'm going to square both sides. But be careful, because on the left side you have kind of a numerator and a denominator you have to square. And you are able to distribute a square over division like that, or over a fraction. It's r squared over 2 squared, which is 4. And then on the right side, the square root and the square cancel just to leave the 5L. And now I think it's not so bad to get L by itself, right? Since L is being multiplied by 5, I'm going to divide both sides by it. So it looks like we're home free, except notice on the left side, this is a complex fraction now. R squared over 4, all over 5. And you know they won't let you leave it like that. When you see a fraction within a fraction, they're not going to want you to leave it like that. So what we can do is just think of the big fraction bar on the bottom maybe as a division sign, and I'll rewrite it. It's the numerator's fraction, r squared over 4, divided by that denominator 5. And then, okay, this is like a fraction divided by, well, if I put the 5 over 1, it's a fraction. So if I flip the second one and I'll multiply, that'll do it. R squared over 4 multiplied by the reciprocal of 5 over 1 is 1 over 5. And now I can multiply across, and I think that'll be good. R squared times 1 is R squared, 4 times 5 is 20. There it is. So that looks a lot nicer than if I left it like this. First of all, the homework wouldn't accept that. They don't like fractions within fractions. But also it looks a lot nicer once you kind of simplify it or make it look prettier. That was a little tricky, I think, because, you know, we had to kind of dig deep back into that rational expressions chapter to see how to simplify those guys. But okay, let's try one more, because this one's pretty complicated, and then we'll move on to the applications, the real-life applications. Alright, so this last example here, we want to figure out, or take this formula, a equals 2 pi r squared plus 2 pi rh, solve it for r. And this represents the surface area of a cylinder. So you can kind of picture like this little blue cylinder I threw in here. It's like a soda can or a soup can type of thing. So I guess a soda can or a soup can, you know, they don't use, it's not filled, it's hollow, right? So if you kind of wanted to measure how much metal or aluminum is being used for this can or this soup can, this would be the formula you'd use. It's the surface area. And if you're kind of curious, I mean, I kind of like geometry. It's kind of interesting. I think this formula, it comes from, you can kind of think of, how do they make a soup can or a soda can? There's kind of like 3 parts to it. There's the top here, which is just a circle, right? And the circle's area is pi r squared. That's the area of a circle. There's also another part on the bottom of the can. That's another circle, which has area pi r squared. And if you combine those guys, the areas combined, you add them together. Pi r squared plus pi r squared is 2 pi r squared. And that's actually where this first portion of this formula comes from. That 2 pi r squared in the front is measuring the area of the top of the cylinder and the bottom of the cylinder. The sides of the cylinder, if you think about a soda can or a soup can, what if you were to cut it along the side and then unroll it? It would end up just being like a flat, kind of like a piece of paper but made out of aluminum. And that guy's area ends up being 2 pi RH. So if you combine the two areas of the top and the bottom, plus the area of this outer part, which unrolls to make just a flat surface, then you get the surface area, which is the total. So especially if you're a STEM major, you know, majoring in science, technology, engineering, math, you're going to see this again if you take calculus, especially calculus 2. We're going to be dealing with these shapes a lot, and it's kind of good to have seen this before, this area. How do you figure out the surface area? Picturing yourself cutting this open and unrolling it. Anyway, so they want us to solve this equation for r, but you notice this one's way more complicated than the previous ones because r shows up here, it's squared, but it also shows up here that's not squared. So it's kind of tricky. How do I solve for r when it's being squared and not squared? Okay, unfortunately, because both r squared and kind of regular r show up here in two different terms, are present, I guess I could say, we must, unfortunately, use the quadratic formula to solve this. So yeah, if you just see your variable occurring once, then it's not so bad. But if you see your variable occurring twice, one time where it's squared and one time where it's just alone with no power, you have to use the quadratic formula. So we need to make this look like, I guess the quadratic formula looks like I would say x squared plus bx plus c equals 0, but our variable is r, because that's what we're trying to solve for. So I kind of want to make it look more like ar squared plus br plus c equals 0. Alright, so it's hard to picture, but this first term here, this is my ar squared, so a must be 2 pi. And this is my br. So b must be, I guess everything surrounding r there, it's 2 pi and the h. So 2 pi h would be b. And then c must be this guy over here. Even though he's not a number, he looks like a variable. We're treating him like a number because the variable we're trying to solve for is r, not a. But notice that that c value, or a, it's on the wrong side. I need it to be on the same value or same side as everything else. The first thing I need to do is maybe get everything on one side. A equals 2 pi r squared plus 2 pi rh. I'm going to move the a over here. Or you can move the guys on the right to the left. It doesn't matter. As long as everything's on one side, then you're fine. And then also in descending order of powers of r, there's the highest power of r, the second highest power of r. You know what you could do too to make it more clear? I'm going to switch the r and the h, so it looks more like something times r, like we see in this term here. And then the minus a must be my c value. So it's really weird, but think of the coefficient of r squared, that's a for the quadratic formula. B is the coefficient of r, which is 2 pi and h. And then c must be this constant term. And don't forget the negative. It's not just a, but negative a. Whew. Alright, so that's the hardest part, is just identifying I have to use the quadratic formula, and then also what the heck am I plugging in the quadratic formula. But once you do that, then it's just plug and chug, or try to simplify it. It'll be negative b squared, or sorry, negative b plus or minus the square root of b squared minus 4ac over 2a. And I'll just replace those values in there. It's going to be weird because these aren't numbers. So I'm going to leave little blank spaces for everything, a, b, and c. Let's see how this goes. Hopefully it works out nice. Don't expect the answer to be really pretty though, because these aren't, this involves variables, not just numbers. It's okay. First is negative b, but b we wrote over here, it was 2 pi h. This is also a b, so there'll be a 2 pi h there. This guy's an a. We said a was 2 pi. And then times c, that was negative a, over 2 times a, which was 2 pi. There we go. So the hard part's over. We're just identifying what's a, b, and c, and what to plug in where. But now it's just simplifying, if we can. There's probably not too much simplifying we can do here. Let's see. I don't really need these parentheses, negative 2 pi h. They're not really there for a reason. Plus or minus the square root of. So we're squaring things being multiplied together here. I can distribute the square. As long as the things inside the parentheses are multiplying, you're free to do that. 2 squared is 4. Pi squared, I don't really know because pi is a number that goes on forever. And then h squared, well, I don't know what h is, so I'll just leave it as is. And then minus, okay, we got a negative 2 pi. Wait, I forgot the 4. Hello. Hello. There's a 4 in the formula. Negative 4 times 2 pi, that's negative 8 pi. Negative 8 pi times negative a is positive 8 pi a. And on the bottom we have 2 times 2 pi, that'll be 4 pi. Hello. Alright, I think that's about it. That looks pretty good. I don't know what else we can do, huh? That's a terrible looking answer, unfortunately. Ugh. It's like, how would that be helpful, right? I guess you could only, how would that be helpful? Only if you, I guess if you knew the surface area of a cylinder, like say you created a soup can or a soda can or something, and you knew how much material you used, you just want to know now what's the radius of this can. Well, I guess if you knew everything else, you could plug everything in here. But I don't know. Seems like it's easier to measure the radius, right? Ah well, this is just kind of, a lot of times these problems, I don't know, they're sort of useful in real life, but not really. They're just more to help you really get the material. If you can do that problem, you can do anything. So it kind of helps you, stretch your brain in ways that you're not used to. All right, but these last couple problems here, they're more like we said, real applications of quadratic functions. Not just, here's a formula, solve it. The first one is back to one of those d equals rt problems. If you remember those guys, you're going to make a little table. You know, just to save room, it might not be a bad idea to make a table up here. Or if you remember, you have a column for each drt. Each of them gets their own column. Then you're going to have 2 rows down below, because there are usually 2 parts of this trip. Notice in this problem they say, during the first part of his canoe trip, Ken covered this many kilometers, and then he traveled blah blah blah. Okay, so it must be, I'm going to label these first part of the trip and then second part of the trip. Then you want to start filling things in. So if you go back to those sections before where we talked about distance, rate, and time, the first thing we said was they should just give you either the distances or the rates or the times. So when you scan through this problem, they say he covered 60 kilometers on the first part of the trip, and then he covered 24 kilometers on the second part. So it looks like the distances is what they just gave us, right? 60 kilometers, that's the distance for the first part of the trip, and then 24 kilometers is the distance for the second part of the trip. And now that we have that, the next thing is there should be some kind of relationship between either the rates or the times. And I noticed in the second sentence they say, he then traveled, okay, he traveled 24 kilometers, we already got that, but the speed was 4 kilometers slower, or sorry, kilometers per hour slower. So that means if we call maybe his speed on the first part x, the speed on the second part was 4 less than that, or 4 slower, so it must be x minus 4. Because remember, rate and speed are the same thing. So his rate or his speed on the first part was whatever it is, x, or whatever you want to call it, r for rate, s for speed. The other part was 4 less than that, which means that minus 4. Alright, we got 2 columns filled in. The very last column, if you remember, you're going to fill in using the actual formula, distance equals rate times time. But since the thing we're looking for is time, that's the one I don't know, I want to solve this formula for t. So you don't really know what you're trying to solve for until you get most of your table filled in. It's only when you have 1 column left, that's when you know, oh, I need to get that guy by himself. And I want to solve for t by dividing both sides by r. Okay, that way time must be distance divided by rate. There we go. That's how we're going to fill in that last column. So for the first part of the trip, the time he took is the distance that he went, which was 60, over his rate, which was x. That must be his time, the fraction 60 over x. And for the second part, same kind of thing. It was his distance for the second part, which was 24, over his rate or his speed, which we wrote x minus 4. Alright, there we go. So we got the whole table filled in. And then the equation we get, I think we mentioned this before when we talked about these problems, the equation we get will be, they should give you some kind of, either an unspoken, or a spoken, they might actually say it out loud, relationship between the 2 times. or whatever the last thing you filled in the table was. In this case, we filled in time last between the times, and that should give us our equation. So, okay, I think the very last sentence does that. It says the total time for the trip was 8 hours. So basically, the total time for the trip means the first part's time, you know, however long you took for the first part, plus however long it took for the second part. Total was 8 hours. But the first part of the trip's time we have from the table, it's 60 over x. That was the time for the first part, plus the time for the second part was 24 over x minus 4. So that's equal to 8. There we go. That's what we're solving. Okay. Whew. And now we're actually back in a couple chapters back where we solved rational equations. Yeah, and this is another one. Yeah, it's a rational equation and our variable shows up in the denominator. So we want to, like we did in that chapter, multiply the entire equation by the least common denominator. And since x is its own factor in this denominator, and x minus 4 is its own separate factor in the second denominator, we're going to need both of them in our LCD. We're going to have to take that and multiply it by each of the three terms, the two on the left and the one on the right. Okay, I should be writing smaller, huh? Let's see, now that'll be, if I want to be careful, you know, I think at this point we've seen enough of these. I think we can just kind of reduce as we go. Notice the first one, the x's will cancel on the diagonal. And what's left is that x minus 4 times 60. But notice, yeah, these x's cancel on the diagonal. But when I multiply x times x minus 4 by the second fraction, the x minus 4's cancel on the diagonal, but the x is left to be multiplied by the 24. And lastly, if I take x times x minus 4 and I multiply it by 8, nothing will cancel. It'll be everything left because there's no denominator to cancel with. So there it is. That's the entire thing. Now to multiply, now the next, oops, sorry. The idea now is multiply everything out and then try to get everything on one side and factor. So I'll try to distribute this 60. That'll be 60x minus 240 plus, we have this 24x here. And if I distribute this 8x in, 8x times x is 8x squared. 8x times negative 4 is negative 32x. Alright, and over on the left I have a couple like terms. 60x and 24x makes 84x. And then minus the 240 that was already there equals 8x squared minus 32x. There we go. Looking good. So now since I see, like we said, we see x squared terms and x terms, I'm going to have to get everything on one side. So move this 84x over here and the 240 over here and then try to factor it. Yeah, this is where we have a choice. You can try to factor it. If you're not too excited about that, you can use the quadratic formula if you want. So I usually make some kind of attempt to factor it, and then if that doesn't work, or I kind of getting frustrated because it's too big a numbers or too difficult, then I'll give up and try to use the quadratic formula. So we got 8x squared. Let's see, these two are like terms. Negative 32x and negative 84x is negative 116x, I believe, plus that 240, that's the only constant term. Alright, I'm thinking these numbers are huge, so factoring won't be fun, but all three of these numbers have a common factor of, I was hoping for 8, but 8 doesn't go into 116. Okay, so 4 goes into all of them, though. If I factor 4 out, 2x squared minus 29x plus 60 will be left. And then maybe that's a little easier to factor, I don't know. We'll see. So that one, notice that if you want to factor that, you have to use the, what's it called? The, that method, the tougher factoring method where you got to go 2 times 60 is 120. That's what they multiply to. They have to add up to negative 29, all that. So I'm going to just say I did that off to the side. You guys can go do it on your own, but we know how to do that by now. So I'm just going to say what the answer. Okay, it'll be 2x minus 5. Oops. And x minus 12. Or if if you start factoring it and then you say, oh my gosh, I can't think of the numbers that I'm looking for, you can just take this simplified 2x squared minus 29x plus 60, and then use the quadratic formula on that. Don't feel like you have to factor. You could use the quadratic formula and you'll get the same solutions we'll get here. All right, now we want to set each of those factors equal to 0. We got 2x minus 5. I don't really have a lot of room here. Sorry, let me kind of scoot it over. Get a little more room over here. 2x minus 5 equals 0. Okay, there's one factor. And then x minus 12 equals 0. There's our other factor. If I solve this guy by adding 5 and then dividing by 2, x is 5 halves, or I guess since this is real life, you could say 2.5. And here if I add 12 to both sides, x is 12. So if one of those values was negative, I could just throw it away because it wouldn't make sense. Because x stood for what? If you look back at our table, x stood for the speed on his first part of the trip. So if one was negative, it wouldn't make sense because there's no such thing as negative speed. But since they're both positive, they're both qualifiers, I might have to see which one works. And the way we'll have to determine it is just see which one makes sense in the table. All the values that we had in the table, like what? Actually, that's, you know what, if you look at the table and you say, all right, one of those values in the table is going to determine which one of these is wrong. The one I'm kind of focusing on is that his speed on the second part of the trip was x minus 4. So what if we said that his speed on the first part of the trip, x, was 2.5? Then his speed on the second part of the trip would be x minus 4, so 2.5 minus 4, which is negative 1.5 kilometers per hour. That doesn't make sense though, there's no negative speed. So that one must be wrong, it must be this guy, 12 kilometers per hour. So again, just because 2.5 kilometers per hour, that's fine, that's kind of a slow speed, but it does make sense. It's just that if you plug it into that second part of the trip up there, x minus 4, you'll get a negative value. So the first part, it would have no problem, but the second part wouldn't make sense. He'd be going at negative speed. So it must be the 12 as the answer for this one. Whew, that was tricky, huh? Okay, let's try example 3. So this one, it'll require us to kind of remember the formula for this guy as well. So don't feel bad if you forgot. Oh my gosh. We did like 2 examples of this a long time ago. But if you're doing work, or 2 people or 2 things are working, then the formula for kind of how they work together or how they work alone was t over a plus t over b equals 1, where t is the speed, or sorry, the time it takes them to work together. I shouldn't say speed, sorry. Time working together. A and B are kind of their times, the people or the whatever these objects are, the times working alone. So time for, I don't know, I'll just say person 1, even though it might not be a person, to work alone. And then B is similar, but for person 2. Time for person 2 to work alone. So kind of as soon as you label what each of those are in the problem, maybe they give you those values or they give you some kind of relationship between them, then you're just plugging them into this little formula here. Let me read this problem just to make sure it makes sense. They're saying 2 pipes are connected to the same tank. Okay. So it must not be people here, it's pipes. Working together, they can fill the tank in 4 hours. Okay. So that must be the time, the little t. Because remember we said t is the time it takes them to work together. So we have that. The larger pipe working alone, okay, that's A. A larger pipe working alone, like we can call the larger pipe the first person, or the first object. The larger pipe working alone, I'm going to label it so I don't forget. Oh, not the first, sorry. The largest pipe. I'll say A is the larger pipe, just so I don't forget which one's which. Can fill the tank in, I was all excited thinking it was 6, but no, it's 6 hours less time than it would take the smaller one. Alright, well I guess if they're referencing the smaller one when they talk about the larger one, I'm going to say the smaller one, let's say he takes X hours or whatever. The smaller pipe. Okay, well that means that since A takes 6 hours less than that, it would be X the speed, or the time it takes the smaller pipe minus 6. Alright, or you could have just left B as B and written this as B minus 6. It's up to you, but I guess we're just so used to using X that it kind of makes more sense to me when I use X. Alright, but now that we have kind of either a number for each of these values, A, B, and T, or some kind of algebraic expression, now I'm ready to substitute those in the formula that we wrote over there. T over A plus T over B equals 1. So we know T, those are both 4. I can go ahead and replace those guys. That's going here and here since there are two t's. But then the value of a here was x minus 6, so that'll go in the denominator of the first fraction. And the value of b was just regular x. That'll go in the denominator of the second fraction. Alright, that's not too bad of an equation to solve, I don't think. I think we've seen worse in this class here. Alright, but this is similar to the equation we got in the last problem. You see that we have a rational equation and we want to solve it for x. But x is stuck in the denominator, so we want to multiply both sides by the LCD, which would be kind of similar to the last one. X, the second denominator, times the first denominator. Or you could have written them backwards, x minus 6 times x. It doesn't really matter. So I'm going to multiply that whole thing by, or that LCD by the entire equation. The first fraction gets multiplied by that, the second one does as well, and then the 1 as well. So I think, yeah, we've seen this so many times, I feel like we're probably comfortable enough to cancel as we go. Let's see here, I'm going to erase this crud here. So if I start canceling, if I think about this guy over 1 especially, x times x minus 6 multiplied by the first fraction, you can see that the x minus 6's will cancel on the diagonal, but the 4 and the x will be left to be multiplied by each other. The 4 that was in the numerator, and the x that was on the LCD here. That was your first term. And now if I imagine this guy, x minus 6 multiplied by the second fraction, I can see that the x's will cancel on the diagonal, but the 4 in the numerator will be left to be multiplied by the x minus 6. And then for the very last part, I'm multiplying x minus 6 by the 1. Nothing is going to cancel because there is no denominator, so it'll be 1 times x minus 6. So it looks a lot better, and then similar to the previous problem, now I want to multiply everything out. There's not much to multiply out here, 4x plus, but here I have to distribute the 4, and I'll get 4x minus 24. On the right side, I didn't even need to put that 1 there, but just imagine I'm multiplying x inside here, or 1x. 1x times x, that's x squared. 1x times negative 6 is negative 6x. Alright, and then on the left side I have some like terms. The two 4x's combined will make 8x. And then there was a minus 24 also on the same side of the equation. On the right side there are no like terms. I'll just rewrite it kind of as is. Okay, and we're almost there. I need to now get everything on one side. So I'll maybe subtract. And of course, remember you want to get everything on the side that's going to keep x squared, the highest power, positive. That's why I move everything from the left to the right. If I move the stuff from the right to the left, the x squared would end up being negative, and it's harder to factor that way. Now there's nothing on the left side. On the right side we have x squared. The two like terms make minus 14x, and then plus 24. Oh, this is way easier to factor than the last one. These are fairly small numbers. Let's see, although I don't even think this factors, huh? Because if it factored, there'd be numbers that multiply to 24 but add up to negative 14. And there are none. So this I would, my idea was factor it. I thought, okay, factor. Question mark. But if that doesn't work, or you get stuck doing it, you can always use the quadratic formula. So that's what we're going to have to do here, unfortunately. Alright, but the a, b, and c values are pretty clear. A is the coefficient of x squared, that's 1. B is the coefficient of x, which is negative 14. C is the constant term, 24. Oops, sorry. Okay, I'm going to write it out, and since we're kind of running out of room, I'm just going to say, imagine you had the quadratic formula in front of you. You should probably look it up or something, but it should look like negative b plus or minus the square root of b squared minus 4 times a times c over 2 times a. And I'm just going to go ahead and fill those in without writing the entire quadratic formula out. B goes here, that's negative 14, so it'll be a negative negative, plus or minus the square root of negative b squared, or sorry, just b squared, negative 14 squared minus 4 times a, which is 1, times c, which is 24. And that's over 2 times a, which is 1. Okay, and then since we're, kind of run out of room, I'm going to move this up to where I have a little more room. I'm going to see if this guy can move up here. So it looks like x is, you have a negative negative 14, which is positive 14, plus or minus the square root of, let's see, 14 squared is 196. Whoops. And then we have negative 4 times 1, which is negative 4. Negative 4 times 24 is negative 56? Wait, no, that's not right. 96. Hello, 96. Ah. There we go. Ah. over 2 times a is 1. Alright. So you got 14 plus or minus the square root of 196 minus 96 is 100. Uh-oh. This is going to be nice values. Wait, did that thing factor to begin with? Oh my gosh, I think that did factor, this guy. Dang it! So, I don't know, just so you know, dang it. If you end up with nice answers, like I can tell we're going to have nice answers because 100 does have a square root. That meant this thing factored to begin with, and I could have just factored it. Oh well, it's good to know it works both ways. Although, just so you know, I mean, you probably noticed this already, the quadratic formula always works no matter what. But factoring doesn't work always. It only works when, of course, the quadratic equation happens to factor. I guess this one did, and I thought it didn't. Dang, oh well. That's okay. 14 plus or minus, okay, the square root of 100 is 10 over 2. And of course, you gotta be careful, you gotta split those into 2 solutions. One of them is where the middle sign is a plus, 14 plus 10 over 2. The other one's a minus, 14 minus 10 over 2. Let's see, 14 plus 10 over 2, that's 24 over 2, which is 12. The other one, though, 14 minus 10 is 4 over 2, which is 2. Oh, these are 2 possible solutions. And again, like the last one, it's not fun because it could be either one. They're both positive numbers. Dang it. Now I got to go back and remember what x stood for. So up here, when we defined what t, a, and x were, x was the speed of the smaller pipe. Okay. So either of these would work, but I think, let's say, usually the smaller one's the one you throw out, in case you're kind of thinking that. We're going to have to throw this guy away because, okay, if that was the speed of the smaller pipe, like, what is it, something per hour? Or the time for the smaller pipe, sorry, hours. Let's say it took the smaller pipe 2 hours to fill the thing. That would mean that the larger pipe's time, like we wrote up there, it's x minus 6. So the time for the larger pipe would be 2 minus 6, or negative 4 hours. That doesn't make sense. So as soon as a solution produces a negative value, when you plug it in anywhere, it's no longer good. So this must be it. 4, and let's see, x was the smaller pipe. So there we go. It takes the smaller pipe 12 hours to fill the pool, or whatever it is, the tank. That's what we should write, huh? It takes the smaller pipe, the smaller pipe 12 hours to fill the tank. And I think that's what they were asking for, so I don't need to really do any more work. Yeah, it says, how long would the smaller one working alone fill the tank? Alright, yeah, so 12 hours. That's weird that our answer for the last example and this one was both 12. I don't know. That kind of freaks me out. Alright, that was pretty fun, you guys. Hopefully you're having fun too. But the last example, this is kind of something brand new that we haven't seen yet. This is an application that you'll see if you have to take any physics classes or if you have to take calculus, which I imagine you probably will if you're a STEM major, huh? Alright, so this talks about, it's very specific. This little formula they're giving us here, it only works in the specific situation where someone's tossing an object downward and you know the initial speed or velocity of it somehow. So let's say, I guess one of those, like, have you ever driven down the road and you see those things that tell you how fast you're going? It's warning you you're going too fast, you know, look, you're trying to go 45 miles an hour in a 40-mile-an-hour zone or something. I guess if you had one of those when you were throwing something and it could measure how fast this thing was going initially. So that's what this variable stands for, v sub 0 or v naught. That's the initial speed of the object as you throw it. It'll travel a distance of s, so that's how far it's going to travel once you throw it. S meters, where, and this is the equation we're going to use. So s, remember, s is the distance it travels. This v sub 0 or v naught, that's the velocity or the speed. And the t that you see in both of those terms, it's the time that's measured in seconds. Time. Yeah, so a lot of these problems, if you ever see this formula or problems like this, all you have to do is really fill things into that formula and then you're good to go. Let's see, there's 3 parts to this. I think they're talking about 3 different situations. So it's just kind of getting us to kind of practice these types. Let's look at part A first. So it's saying a coin is tossed downward with an initial velocity, okay, that's the v sub 0 or v naught, of 30 meters per second from an altitude of 75 meters. Okay, well I guess that means S must be 75, right? Because it's saying you're tossing it from an altitude of 75 meters, and it's going to hit the ground later. They want to know when it hits the ground. So I guess picture yourself, you're here. I don't know what you're doing. You're standing on something that's 75 meters tall. An altitude of 75. And you're throwing something downward, and it's going to land here. So it traveled 75 meters, right? That's your... Because that's what S stands for. S is how far it traveled. So we got those, and it wants to know approximately how long does it take the coin to reach the ground. So I guess that's all they give us. I must be using the formula that's in the box. It's S equals 4.9 t squared plus v0 or v naught t. S, we already know they were given. It was given to us. It's 75. 4.9 t is something we don't know because that's what they're asking for. How long does it take? So what's the time? And then the initial velocity was 30. Alright, so we want to solve this for t. That would mean this is quadratic in form too. It looks kind of like ax squared sort of, or at squared plus bx or plus bt. And c though is on the wrong side. I think what I need to do is get everything on one side and either try to factor or use the quadratic formula. And looking at the value of A is 4.9. I don't think I'm going to be able to factor with that guy. So I think our only choice is to use the quadratic formula. 4.9 t squared, that would be plus 30t minus 75. That's going to be interesting. So yep, we'll have to use the quadratic formula there. And since it's in order, I can kind of tell A is 4.9, B is 30, and C is negative 75. So I'll plug those in the quadratic formula. Negative B plus or minus the square root of b squared minus 4 times a times c over 2 times a. Alright, let's see. The value of b is 30. Here's another b. Minus 4 times a, which is 4.9, times c, which is negative 75, over 2 times a, which is 4.9. We'll try to simplify this guy as much as we can. What do we have? So t is negative 30 plus or minus the square root of, okay, 30 squared is 900. And after that we have a negative times a positive times a negative. That's a positive. 4 times 4.9 times 70. That's 1,470. Don't feel bad if you use a calculator on that one. Oh my gosh. Seriously. Over 2 times 4.9, that's 9.8. Alright. And this one, you know, a lot of times it's an application, so you don't feel bad if you use a calculator all the way through. Let's see, 900 plus 1470. I'm going to do that on my calculator. It's 2,370. And I'm not even going to try to do that square root in my head. I'm just going to, you know, do my best to do that on the calculator. The square root of that guy, and you can, don't worry about rounding. If you do this on the homework, they'll probably tell you where to round. It's 48.7 or so, that square root. Alright, so this represents two different solutions. One of them is one with the positive in the middle, negative 30 plus 48.7 over 9.8. The other one is when you have the positive in the middle, the negative in the middle, negative 30 minus 48.7 over 9.8. And if you simplify those, the first guy, if you combine the numerator, that's 18.7 over 9.8, which I imagine is around 2. 18.7 divided by, it's 1.91 or so. Or the other guy, you're going to get a negative number. Let's see, 48.7 divided by 9.8. It's about negative 8.0 or so, if you round it to the tenths. But what does this stand for? This is time, right? There's no such thing as negative time. So this must be the guy. It must be, it took the coin 1.19 or 91 seconds to reach the ground. There it is. Whew, it's kind of tricky, right? But it's good to know that this can be used in real life, sort of. You know, when you're throwing things at people on the ground. That's messed up, but hey, people do things like that. Alright, so part B and part C I imagine are going to be sort of similar. Let's see, part B says, a life preserver is dropped from a helicopter at an altitude of 75 meters. Okay, let me see, part B. So 75 meters, that's the same altitude as part A, huh? So that must mean So it's dropping all the way from that height to all the way to the water or the ground. So that must be how far it goes. From the altitude all the way to the ground. And then what? Then, that's all they say. Approximately how long does it take the life preserver to reach the water? But you notice, in this example, I don't see a velocity. They don't tell me the initial speed. And this one's kind of tricky because it's actually kind of given to us, but they do it unspoken. Because notice in part A they say a coin is tossed. So someone's thrown it, and that's why it has an initial speed, because you're throwing it. But in part B, all it is dropped. So the initial speed's actually 0 in part B. Because it was just dropped, not thrown, you know. It wasn't thrown, so there was no speed. It's like, imagine if you're watching a baseball game, and you know, usually when the pitcher throws the ball, they measure how fast it was going. But what if he didn't throw it, he just dropped it on the ground? Then it wouldn't have any speed, it would be 0, because it didn't even go anywhere. So it's kind of like that, the speed of this thing is 0. So I'll do something similar, but I think this will make the problem a lot easier. So the formula we're supposed to use is the same one from the box. S equals 4.9 t squared plus initial velocity times t. Okay, the S was 75 equals 4.9. Of course, time is what we don't know, so we're leaving that as is. But the initial velocity was 0 because, again, it wasn't tossed, it was thrown. Or, sorry, it was dropped. And 0 times anything is 0, so really we just end up with 75 equals 4.9 t squared. And that actually made it way easier because now t doesn't occur twice. In part A, the hard part was you saw t twice, it was being squared, and it was all by itself. So we had to use the quadratic formula. But now that t only occurs once, we can just isolate t. That's going to be way easier, no quadratic formula necessary. If I want to isolate t, I'm going to divide both sides by 4.9 first. I have to do that on the calculator. Don't feel bad if you use a calculator for that guy. Do not be a hero. It would be, and if you round it to the 10th place, they'll tell you where to round it. I'm going to imagine they're saying 10th place. It's 15.3. And we almost have t by itself. We just need to divide, or not divide, sorry, square root both sides. And I should put a plus or minus here, just because we know when we square root both sides of an equation, we're supposed to put a plus or minus. And on my calculator, let me see, I'm going to do the square root of 15.3. It's about 3.9 if you round it to the 10th place again. Alright, but this is really two solutions. It's t is positive 3.9 and negative 3.9. But again, time can't be negative, so if I had actually forgotten the plus or minus, I'd be okay. So it must take that life preserver 3.9 seconds to hit the ground. That's not too long, I guess, huh? 3.9 seconds. Well, if you're drowning, that probably seems like a long time. Give me that dang life preserver to hit the ground, or the water. Did it say water or? Oh, water, sorry. Whatever, I'm not paying attention. Water, there it is. Beautiful. Alright, so I think this one, it's almost like I should have done those two parts backwards, huh? Because part B was way easier. Sorry, guys. I think part C will be easier than part A as well. Don't worry. So what does part C say? Approximately, how far will an object fall in 2 seconds? So notice this one. This is the first part where they're actually giving us the time. So t is 2, because that's time. If thrown downward at an initial velocity, okay, that's v sub 0 or v naught, of 20 meters per second. Alright, so it looks like this time, instead of, like in part A and part B, they give us s and v, this time they're giving us t and v, so we must want to know what s is. But we'll do the same thing. We're going to take the formula that they gave us in that box and replace everything we know. Once we replace everything we know, we'll solve for whatever's left. So s we don't know. That'll stay as is. The t squared, I'm going to replace t because I know that. Also, I know the v0. So t is 2. That means 2 is going to go here where t was and here where the other t was. And the initial velocity was 20. That goes here. And notice all we have to do now is kind of plug everything on the right side of this equation in our calculator and we'll have s. But be careful because you have to use order operations. I can't do 4.9 times 2. I have to square 2 first, that's 4. And then I'll multiply that by 4.9. And here it's 20 times 2, that's 40. That's 4.9 times 4. Don't be a hero. Use a calculator. 19.6 plus 40, that's going to be 59.6. And remember, this is how far the thing fell, so I'm going to see what kind of units were they talking about in part C. They were talking about meters, right? Because they said the velocity was 20 meters per second. Okay, so this must be in meters. Okay, that means, what was this object? Oh, it just says object. The object fell 59.6 meters. There we go. Perfect. Alright, so this section was definitely tough. It kind of got us back for how easy the previous section was. But in the homework, there's not too many problems like these last three here. I think they're mostly like those formula ones, if that makes you feel better, I hope. And these are pretty difficult. I think, you wouldn't really be expected to solve these really complicated ones on an exam. They're just more, it's good to have seen them because you'll see them again in the future. It'll, kind of the more times you see a problem, the easier it'll get the next time you see it. That's kind of why we introduce it early, even though it's really complicated and tough. But they're kind of interesting, I think. Alright, well, I'll see you in the next video. I mean, definitely the hardest part of this chapter is over. The first section was really tough because of completing the square. This section is tough because of word problems and applications. It's kind of smooth sailing from here. I think you'll like it. So, alright, thanks for listening. I'll see you in the next video.